Hi, I'm Steve Rosted, and today I'm going to be talking to you about how to analyze your virtual machine's overhead compared to bare metal with tracing. A little bit about myself. I recently joined Google back in January. Back in 2004, I helped create the PreemptRT patch set. I'm also the creator and maintainer of ftrace, which is the official Linux tracer of the Linux kernel. And I'm also the creator of make local mod config, something that you might want to use if you ever want to remove all the modules when you build your that you're not using when you build your kernel. I'm also the creator and maintainer of ktest.pl, which is a Linux kernel testing framework that's inside the kernel. But let me get right on to what I'm going to talk about. So, using virtual machines. The advantages of using a virtual machine is gives you a lot more flexibility. For one thing is if you want to upgrade a machine, you could actually migrate it to another machine. So you either have a new upgraded machine, or if you want to upgrade the one you have, you can migrate to another machine so it's constantly online, and then you could update the other machine and migrate it back. You could duplicate VMs for redundancy. You could do snapshots for archiving. They're easy to shut down and reboot because you don't have to go through the hardware BIOS. And they're considered more secure. I say that in quotes because, yes, there's issues where you can get from the guest to the host and whatnot, but it raises the bar on what attackers have to do to infiltrate your machines. So, what are the cons? One thing is it takes up more memory. You need a kernel for the hypervisor as well as for the guest OS. So this adds overhead. Also, there's indirection that the VMs need to get to the devices. So how bad is this really? Now, the pros usually outweigh the cons, so that's why people still use VMs. But you really want to make sure you want to get the most out of your virtual machine, so you try to look at your systems to see how you can improve it. And where can you improve the virtual machines? Well, anytime the virtual machine has to go to the host to basically ask it to do something, that's usually overhead, because on bare metal it would just do it itself. But if it has to be emulated or whatnot, it takes a little bit more time, and that adds more overhead running on a VM than if you ran on bare metal. There's also VirIO devices, which is virtual I/O, which takes advantage of the fact that it's a virtual machine, whereas the virtual machine will say, okay, I know I'm a virtual machine, and let's try to have ways of sharing memory with the host so we can eliminate things so the host doesn't have to actually emulate real hardware, which means you have to emulate all the quirks that come with that. So, how do you determine where the virtual machine overhead is? Well, as I'm the ftrace maintainer, I'm going to obviously use ftrace for my solution. Specifically, trace-cmd or trace command. This is a front-end command line interface for the ftrace infrastructure in the kernel. You could start tracing and examine the traces within the kernel, and you also record to a file the traces from the kernel that you could do post-processing. And this talk is going to focus on that post-processing. So when I was creating this talk, I figured out I need to have examples to use. So I looked around for benchmarks that are common that people would be aware of, and I came across sysbench, which is something that's used quite a bit. It's available in most of the distributions. It has a MySQL benchmark, and since a lot of the use cases of using virtual machines is for databases, having a database benchmark would be appropriate. And it's good it's a good benchmark to compare different machines. And since I'm comparing virtual machines with bare metal, I decided to use this. The database I'm using is MySQL or MariaDB. And just because I'm using both Debian and Fedora in this talk, I noticed it was kind of interesting that the Debian database server was called, the tasks were called mariadbd, whereas on Fedora it was called mysqld, but the actual code was still MariaDB, so they're both using MariaDB. Just have to remember that when we actually analyze the trace data, to remember that if it's on Debian, it's MariaDB is the task name, and MySQL on the other. My setup, I ran this on two different machines. Now, I'm not comparing Fedora to Debian because the machines I'm running on are completely different hardware, and you can't really compare them as apples to apples. That'd be apples and oranges comparing that. But what I want to compare here is looking at two different setups where there's comparing the virtual machine with the bare metal and the host. So what I did was on the Fedora side, I made sure that the Fedora VM on the Fedora machine was the same setup as the host itself. I did the same thing on the Debian, which is the Debian testing I did a checkout from a month ago, and I did it for both the, I upgraded my host and I upgraded the guest, so it would be basically the same operating system. And then for both machines though, since I made the virtual machines only, or I have 4 CPUs with 2 gigs of RAM each. Here's a visual for my setup. It's nothing really big. It's just the fact that you can see that I have the Fedora machine and I have a Debian machine, and they're running a Fedora VM and a Debian VM, respectively. The setup, to make things even, I decided to make sure that all the test cases and all the database servers were running on a single CPU. So I used the task set utility to assign each of these processes to a single CPU. I assigned it to CPU 1. I usually suggest if you're going to do something like this and assign it to a single CPU, that you would assign it to CPU 1 and not CPU 0, as CPU 0 is sometimes used by the kernel for housekeeping tasks. I didn't want those to interfere with my tests, so I make sure everything's assigned to CPU 1. The database server I made sure was assigned to CPU 1, as well as the benchmark that I ran was assigned to CPU 1. And how did I do that? Well, first thing I did was I find out where the database server is running. So I searched on Fedora, I searched for mysqld, and I found the process ID, 20539. And then I ran taskset -a-pc1 to 20539. And what that says is -a means include all its threads. Although I only did ps-aux, that process for MySQL actually has several threads running. So if I left off the -a, I'm only pinning the one thread to the CPU. And it'll have lots of other threads that could run on any CPU. And actually, when I first ran my test, I noticed that things were not, wasn't what I expected. And I realized, oh wait, why are these threads running on other CPUs? And I realized, oh, I didn't use -a. So I had to make sure I pinned everything to that one CPU. So when I ran the sysbench on the guest, this is the Fedora Guest run, I ran it under the task set utility as well. Still passing in -a for making sure all threads are pinned to a single CPU. -c is saying what CPU do I want to pin to, and CPU 1 is the number I want. And then I ran my full command, specifying the MySQL driver, so it ran the database test. Other options, not really, it's just pretty kind of self-explanatory. I made sure I had 4 threads, and I only ran it for 10 seconds, just for this demo. I did the same thing on the host, and this just shows you that. And at the end, I was able to take a look at the differences between the results at the end that the sysbench gives you between the host and the guest. And I noticed that the guest ran 6% slower than the host. So the overhead of the virtual machine for sysbench on this machine, in this case, was 6%, which is actually not that bad. The latency part was about 6% slower, which again isn't that bad. So I did the exact same thing on the Debian side. Of course, I searched for mariadbd. I left that part out, and ran it on the guest and ran it on the host, and then I looked at the comparison. But this time, I noticed it was 25% slowdown, which was much larger than I expected it to be. So there's obviously something different about what's going on with the Debian use case than with the Fedora use case. And it had a 34% more latency involved as well. So how do we analyze all this? Again, I said I'm going to use trace-cmd. And luckily, KVM, the kernel virtual machine utility that what Linux as a hypervisor runs, has over 100 events that it can use to examine this. And these events are triggered when it tells you what KVM's doing to handle the guests. It tells you when a guest exit, which means, so when the guest is running as a guest and needs a host, it's going to call something called KVM exit that will exit down to the host, and then the CPU will switch back to the host, run as a host mode, do some work, maybe emulate a command or something, and then it'll switch back to the guest and let the guest run. And in that case, another event is triggered called KVM entry. So we get to see why the guest exit and what the host is actually doing when it does exit. So to record this, I run trace-cmd record, and I'm going to use the -E option to trigger enable a bunch of events in this record. So I'm enabling the scheduling events. So sched will enable all the events that have to do with scheduling, and kvm will enable all the events that have to do with kvm. I get specify individual events as well, but I figured I'll just grab them all. It's a lot easier and keeps the slide smaller. Then I run the ssh command to SSH into my virtual machine, and I run the exact same command that you saw on the previous slide. So what this happens is it's going to SSH into the guest, it's going to run that command and record the tracing of the host. So the host events will get to see all the events that are happening on the host, and when the command does, the tracing will stop. And when I'm done, it will be saved in a file called trace.dat, where if I do a trace command report, which by default looks at the trace.dat file, it will show me all the events. Now, looking at this, it's great. I see a bunch of scheduling events, I see some kvm events, and that's great. But unless you're a tracing expert like myself or not, it's difficult to know what is actually happening. You have to actually look at all the events. It's one of those cases where there's too much info, and too much information can make it harder to find things than not enough information. So I want to talk about this library, libtracecmd. It's something I've been working on. It's been released, and hopefully everything that I've talked about in this talk will be also released by the time this talk comes out. And it's a library that comes with trace command that lets you basically analyze the trace.dat file that trace command record creates. And this talk is not about that library or how to use that library. It just is here to tell you that it exists. But this talk is going to show you one of the tools that I wrote that utilizes this file, which is called kvm exit. The link below is where you could get the code. I have a bunch of comments in there to let you know how to use it. The idea is to let you know that this library exists, download the code, tweak it, and do what else you want. If you have questions, email me. I'm happy to help. So what this tool here does, looks only at basically the kvm exit and kvm entry events. So when I run it on the trace.dat file, it gives me a bunch of information now. It shows you all the events that's happening and then breaks it up per CPU. Now, even though we pinned the tasks running on CPU 1, because I just did a full record of all events, I get all events from every single virtual CPU. So I see virtual CPU 0, and the only thing for saving of the space of the slides, I'm only showing virtual CPU 0. And it shows you which process on the host runs for that virtual CPU, because each virtual CPU is mapped to a thread on the host. And that's process ID 2442. It tells you the number of times it exited from during this run from the guest to the host, which was 32,000 times. How long it was, which was over 8 seconds. It was exited the host before it came back. And it gives you average time and a few more information. That's pretty self-explanatory. I do want to state that I had everything's in microseconds except for the min time, which is in nanoseconds. That's because when I ran this, the min time was always 0, which was kind of useless. So I switched it down to be more to nanoseconds so you could see how long the minimum time actually was. Then it breaks it up into the reason why it exited each time. So the first one here is it shows you that NMI happened, and that happened exited once. And it tells you how long, few external interrupts, there's 5,000 external interrupts. Goes down to interrupt window is a pending interrupt exit. CPU ID is anytime the processor executes a CPU ID, it'll exit to the host, so it lets the host determine what that CPU ID is for the guest. But I also noticed in this run that the halt expression is. Halt exit happens when the guest wants to go idle and not do anything. So it was idle for 8 seconds during this, for a total of this run, not 8 seconds in total, like consecutive, but in total, even though maybe it only ran for 10 seconds, the application probably ran for just 2, and it was idle for 8 seconds from there. So I really don't care about this. So how do I eliminate this information and only see what I actually care about? So another thing you do is trace command agent. Trace command agent can be run on the guest, and this allows you to connect the guest to the host and synchronize the event and trace the guest as well as the host. So the way it does that, it creates what's called a virtual socket or vsocket, which the vsockets are sockets that are defined for each guest. And this way we can start tracing on the guests and synchronize timestamps. So when you do the record in trace command record, you pass in the -A option, which means agent, which means it's going to connect to one of the agents that's running on a guest. And it will tell that agent to say, okay, start tracing, and pass that tracing data back down to the host. And this way, it also do the negotiation of timestamps so that the timestamps are synced when you actually look at both of the trace files, because this will create two tracing files, one for the host and one for the guest, that you can look individually, or if you put them together, it will synchronize and make sure all the timestamps are the same. So how do you run it on the guest? Well, simple. You just do trace-cmd agent, and it runs. If you pass in, I guess there's a D option to run as a daemon mode, and it'll tell you listening on at4:823. Well, what does that mean? Well, at4 is the context ID of the virtual socket. Now, think of it as like an IP address for networking sockets. So these sockets are for guests and the host. So the host is assigned a context ID, and each guest will be assigned a context ID. So to talk to that guest, you actually have to know the context ID of it. So that's why you're going to need to know what this guest is. That's this number. So you know the virtual socket. The port number is just like a port like TCP or UDP on a networking socket. So to connect to a virtual socket, you need the context ID and the port to connect to it. On the record side, I do the same thing as I did before, the trace-cmd record, but I also add that -A with the at4 and 823 to specify what guest I want to connect to. I also give it the -name guest because this will create two different files. I said trace.dat for the host, and it'll be, if I left off the -name, it would be like trace-4.823, which isn't very human readable, and I'd rather have a human readable name for the guest name. So if you put name guest, it will change the trace.dat file or to be trace-guest.dat. And then everything after this is the commands that I'm telling the guest to do. So that -e-sched is telling the guest enable all scheduling events. There's no KVM events up on the guest I have to worry about, so obviously I leave that out. And then again, I do the SSH to get all, or tell the data, or tell the guest to run the benchmark. And after that, that KVM exit that I'm running is now I'm going to specify some more information. -c sysbench means I'm only interested in the sysbench application running on the guest. So -c is com, which is a command line name. And here I have to pass in the two tracing files. So one is the host and then the guest file as well. And now it only shows me information when the guest is running, or guest is running sysbench. So it'll ignore all KVM exits except for when the guest is actually running sysbench. So those halts, those idles, those are all ignored. So it tells you virtual CPU 1 because it was pinned to virtual CPU 1, so it only shows me virtual CPU 1 in this output. It exited only 2,000 or 2,500 times, and for a total of 16,000 or 16 milliseconds. And I get the same thing with the interrupt. A penny interrupt happened when I was running it. A few MSR writes, well, 600 some MSR writes were done. But there's this EPT violation, which is the extended page table violation. So it's something I may want to look at because I'm like, okay, why is this happening? And I want to look at maybe it's something I could fix in the setup so it does less of these. Now that was just a sysbench application. Now let's look at the mysqld application. And I ran this too, and it was actually it was 66 milliseconds out of the guest. And here it not only had a extended page table violation, it also had extended page table misconfiguration for 3 milliseconds worth of time. And here's something again, I might want to look and investigate this. Now let's do the exact same thing on Debian. So I did the exact same runs before I connected to the tracing, and when I looked at sysbench, a little bit longer. It was 26 milliseconds out. Same EPT violations for 13 milliseconds. And then when I did the mariadbd application, remember it's not MySQL on Debian, it's mariadbd, which is the name, which it was out for 132 milliseconds. That's quite a bit longer. And it also had the two types of extended page table issues. One was for 48 milliseconds, the other one was 18 milliseconds. And another little thing I added to my KVM exit application was if I add the -f option, it does even more work. By the way, you're going to need to have all the latest and greatest libraries, so libtracecmd, libtracefs, and libtraceevent, which are all available, and I'll have links for them later. They're not in the slides, but I'll make sure they're available. And when I run this, not only does it tell me the reason why the EPT violation happened, it actually will look at the guests because on the exit, it tells you where in the guest it exited. And if that data or that IP address of where it exited from the guest happens to be a kernel function, it will show you what kernel function it was. And if it happens like if there's lots of kernel functions, it'll break it up per function you have. And it just, in this case, it just happened that that APT violation that happens in the same spot every single time. And it's at that mem/cg/post alloc hook function. So something I might want to look at to say, is there some way I could keep this violation from happening? And the misconfiguration is happening on the IO write operation. So I also created another little application to analyze just the tasks that are running. Now this is not related to virtual machines, the KVM exit, KVM entry, but it's about just what happens in the time of the tasks per process. It examines a task on which CPUs it runs on. It sees how long it's been preempted, which means a higher process came in and stopped it from running, so it wants to run but can't because there's other processes running. It shows you that. It shows you when it's blocked in I/O, which means that it's waiting for some I/O to happen and it can't go on until it receives data. It also says when it just sleeps, like where, okay, I have nothing else to do, so I'm just going to schedule out. So when I ran this on the mariadbd trace.dat file on Debian, I noticed that it was actually blocked for over 2 seconds of the runtime. And here I ran it, that was for the host, and for the guest, it was run, if I have that right, so 3.352464, so 3.5 seconds, or 3.3 seconds, or 3.4 seconds on the guest. So it was blocked for 33% of the run, and because it has a full runtime, how long it was running at the top there. And on the guest, it was blocked for 47% of the time. So I can now know that there's probably some I/O issues that's happening on the guest that's not happening on the host. And this gives me an idea of where to look. Finally, I just want to do a shout out here. So if you want to visualize the data from the guest to the host, I have a little tutorial link. I don't have time to talk about how to set this up, but the trace.dat files I have from the host and the guest, if you run kernel shark with trace.dat with the -a, which means append to trace-guest.dat, it gives you a nice little visual of the guest. So all the sysbench applications are running up there. So I was able to trace or plot just the sysbench applications, and down at the bottom you can see CPU1, which is this guest CPU1, and then the host underneath it. And when you see the line that goes down and the line that goes up, and those two lines that shows the distance here, that's shows you when the guest actually exits to the host and back again. And down at the bottom you see all the events that actually happen, so you actually examine it more. But that's for another talk. Anyway, thank you. That's all I have to say for today. Thank you very much. My name is Steve Rosted. My contact information is here. My Twitter handle is @Rosted. And thank you.